Good afternoon, GEO 1010 students. Apologies for this April 3rd snowstorm, but given the safety of the road conditions, I've decided to deliver this lecture via an online recording in my YouTube channel. And so we'll be back on campus on Wednesday, and we'll have an in-class activity about some of the concepts that we're talking about here. We'll also have time for you to ask questions and address anything that you wanted to bring up after watching this lecture. So today we were talking about Chapter 12, Riches in Rock, Energy, and Mineral Resources. And on this first slide here, I have world population growth over the last several hundred years. And so we can see our population is exponentially growing for some time, although it may be kind of at this kind of inflection point in the curvature of this trend. Here we are today at 2020, we're actually over 8 billion people now. But over the next 50 to 100 years, we should start to level off in terms of population growth. Somewhere between 11 and 12 billion people on Earth will be kind of our sustained population as the projections show. And it's probably good that it's leveling off, given that's 50% more people than we have on Earth today. And we're already, in many cases, kind of reaching a point where mineral resources, energy resources are in such demand that prices are increasing skyward. And so we need to kind of have a good balance between number of people, their energy demands, hopefully can be minimized, their resource demands minimized to meet the needs without sacrificing also the wonderful natural landscapes that we have and the ecological functioning of those landscapes, not just for people, but for the whole ecosystem. And so, yeah, we do have kind of a carrying capacity of our planet, and we don't want to exceed that. And so this chapter, we'll be talking about these resources, some of the limitations that we face with these resources, and how the resources form. So we use a lot of geological materials. First, let me say that all of the materials we use come from the planet Earth. Therefore, they are, by and large, produced by geological processes. And so here, this is a little table from your book, yearly per capita, per person, usage of geologic materials in the USA. So this is the amount of stuff that is used per person in the USA for you. Do you use 4,000 kilograms of stone every year? No, but the bridges, the foundations, the roads, for all the municipal buildings, the military uses, transit ways, that's your share in here. 5 kilograms per person of zinc, 6 kilograms of lead, 10 of copper, aluminum 25 kilograms, etc. Clay used 220 kilograms. So these are really basic things. We all use a lot of them to keep society functioning. Many of the resources that we use are not so readily available. And so good question is, how long will these mineral resources last? For instance, iron. We know from looking at the mineralogy of rocks that there's a lot of iron and aluminum in the Earth's crust, and certainly iron even more in the interior. But that doesn't mean that we can easily access it for making things like steel and other uses of iron. We need to get it into a format that we can utilize. And so we mine what's called ore, whether it be copper ore, like is found in Utah's Bingham Canyon copper mine, or a lead ore, etc. These are situations in the geology where that mineral, iron, that element in this case is wrapped up into minerals that are accessible economically to be produced. So if the iron is within a mineral, but it's not easily to be separated from that, then it may cost more to separate the iron than it's worth on the open market, which means it's not an ore mineral. And so ore minerals are ones that are economically viable. And so, or ores in general, ore bodies of rock. So if we look worldwide, we have 120 years of worldwide reserves of iron ore known. 40 years for the US only. And so, of course, if we look down the US reserves for some of these important things, we don't have chromium reserves or manganese reserves in the US. Even we don't have much aluminum reserves. Aluminum, by and large, is often coming out of tropical soil minerals, and we don't have tropical soils here in the US, so we don't produce aluminum. And so we need to rely on the world as a whole. And this shows, right, the planet in terms of the mineral resources we use, it has a carrying capacity. We need to rely also on each other countries, to function as a society in this industrial and kind of digital age where many of these materials are needed by everybody. So cooperation is important. And also, on the other side of things, to find mineral ores, it takes geologists time to figure out where in the earth these are going to be preserved in a way that they've been kind of prepared by the prior geological processes to be easily extracted. And so that's the job of geologists. One of the jobs, right, is to help us find where these things are in terms of structural geology, and then when they've become in the right kind of mineralogy and chemistry to be extracted from the processes that it experienced, whether that be magmatism and hydrothermal fluids or some sort of fault zone process, etc. So that's a big function of geology. Okay, so first thing we're going to talk about is energy resources, and particularly fossil fuels. So just a definition of energy. Energy is the capacity to do work. And so work is force applied over a distance. Force equals mass times acceleration. That stuff you remember probably from an introductory physics class in high school. But generally, we're speaking about in terms of fossil fuels, and these fuels is either doing work in the case of hydroelectric, kind of pushing a turbine by wind or water, or converting chemical bonds into heat energy, such as with fossil fuels. And that energy can do work and can be delivered across the grid to everybody. Or in the case of fossil fuels, one of the beautiful things about them, like oil and natural gas, is fairly portable, given some limitations, of course, of safety concerns. So if we look at this graphic on the right here of energy resource use and produced, so energy produced in terawatt hours is the y-axis here, and time is the x-axis. And so we see that originally, go back to the 1800s, most things were biomass, so burning wood or peat. But then we start to take advantage of geological materials, i.e. materials that are preserving past biological productivity on Earth, such as coal, oil, and gas, fossil fuels. We start using those in the 1800s as a part of the Industrial Revolution, but also because we became much more advanced as a field of geology and determined how to find these resources in the rocks. So coal is past life, formed in most cases millions of years ago from woody material. Oil and gas comes from photosynthesis activity in water, in the oceans and large lakes, where little phytoplanktons and zooplanktons in the water column have lived. They've been deposited after death onto the seafloor, but in a way that they didn't become like biodegraded in terms of bacteria and things. And so it's preserved within the rocks and then later converted into oil and gas by some certain pressure and temperature conditions during burial. And so those are fossil fuels. And then what we see is we know that those fossil fuels are limited resources. So the fossil fuel age is something that we live in. And we're kind of near the kind of peak probably production of those fossil fuels, and that will decline over time. I believe the projection is that these fuels will be available to us for a couple hundred more years, but they become harder and harder to find with time. And so we need more sustainable, renewable energy resources, not just because it's better for the environment, since fossil fuels cause significant pollution byproducts, but also because we will run out of them and we need society to go on. Not only that, we need to have society go on with 50% more people than we have on Earth today. And so we've been over a long time developing hydroelectric electricity, probably kind of getting near the capacity of that, although we are doing a lot more with trying to deal with energy and trapped energy from tides and currents in oceans, not just rivers. We're adding a lot of wind infrastructure, biofuels, although they tend to take pretty hefty input of fossil fuels to produce. And then geothermal, something that we're probably not tapping into nearly enough, given that the heat of the Earth is down underneath us pretty much everywhere, although in an economical sense, only in areas where the geothermal gradient's a little high. And then solar energy is rapidly rising as well. So we talked basically about this in the last slide, several fundamental energy sources available to us on Earth. And so I've lumped these into 6. Your book has a few more, but generally I just say we have solar radiation. So that can be direct to your solar panel and converted to electricity, or it can go into like basically lifting water, evaporating, getting winds to move and things like that. So it's like a secondary effect of uneven solar heating. We change the air masses and move them around. And then, of course, we produce, organisms use photosynthesis, take advantage of the sun, and that leads to biological productivity. And we can convert those biological chemicals into energy through incineration, amongst other possible ways as well. But basically, that's chemical bonds changing. And so we can release energy in that way. And we can do that for living things that died this year, or we could do it for things that were buried millions of years ago. And that's what we're talking about with fossil fuels. And then I've thrown in gravity here because, and that's related to tectonics, lifting mountains up, but then the sun moving around water on Earth allows us to have hydroelectricity. And then we have things like we can take advantage of other things like chemistry-wise, we can use nuclear fission reactions and perhaps someday also fusion reactions. And then we have the internal heat of the Earth from radioactivity and just the general heat of formation. And that energy can be taken advantage in terms of geothermal energy in areas near kind of magmatic areas, and then just also areas where the temperature of the Earth is a little hotter than usual, where there's favorable conditions of bringing hot groundwater from deep under the Earth towards the Earth's surface more rapidly than normal. So yeah, I've lumped it into 6. Your book has a few more. Okay, so let's talk about fossil fuels, and we'll start with oil and gas. And so we refer to these as hydrocarbons because they're made of hydrogen and carbon, and they derive from materials that were once composed as living creatures. And so there's many types of hydrocarbons which are found in nature, but we'll just talk about oil and gas, generally lumping these together. And so when we talk about oil, we're thinking about the gas you put in your car. It's not gas; it's a refined oil product. Gas is literally gas, fluid in a vapor form. And so that can be compressed and stored and utilized and put along pipelines and things like that and transported to where it's needed. But where does this stuff come from? So oil and gas comes from marine organisms, things that we find in water columns responding to photosynthesis. So we have phytoplankton and zooplanktons and living in the water column. And over here on the upper right, this shows you the log of abundance, how much stuff is there in the ocean, and then body size. So big things like fish, well, you think there's a lot of fish in the ocean. Well, it's nothing compared to this logarithmic plot. So there's much more zooplankton, small little microorganism animals, and small little microorganism phytoplankton, plant sort of creatures. So these things, phytoplankton, algae, zooplankton, they're taking advantage of photosynthesis and metabolizing things, storing energy in their chemical makeup, and then they die. They fall to the seafloor and they get trapped in the sediments. If they get trapped at a high rate in a particular sedimentary layer, and usually that would be fine grain, low energy marine environment, like the rocks that we get out of that are shale, kind of mudstones, but most likely organic rich shale, you might call it oil shale even. That is buried eventually by the geologic process of additional deposition. If we put it under high enough pressure, it will basically begin to change its composition from just those buried organic items, the phytoplankton and algae and the minerals, but it will be kind of pressurized and turned into this waxy substance, such as kerogen, at about 80 degrees Celsius. And then as temperature continues to increase, kerogen can turn to oil. Oil is less dense and tends to be buoyant and move upwards. If you increase it even hotter than that, it may become gas. And that's also likes to move upwards. And so we kind of have these windows of temperature where we produce the precursor, kerogen, and then oil, and then gas with just sedimentary burial. Okay, so burial that we need to get to is about 2 to 4 kilometers to basically take the sedimentary rock or sediments and turn it into this black shale, which has this oil shale, has this kerogen within it. If we continue to heat that kerogen, it's further broken down to oil and gas, and those things are buoyant and they move as fluids upwards within the pores of the rock. They can be stored in rocks that are more porous, like sandstone. And so those sandstones become good, what do we call, like oil reservoir rocks. The source rocks tend to be those black shales, and they have a lot of petroleum hydrocarbons, but it's not very good for storing oil, also or extracting oil from, because it is not very porous and it's hard to get that material out in an economical sense. And so sometimes we do it, and that's called fracking, when we create kind of conduits for natural gas to make its way through the source rock. The source rock, that clayey shale, is just too resistant to flow. And so we need to, by natural geologic processes, we need that oil and gas to move into a rock that is more porous and material moves through it more easily, like a sandstone. So the oil and gas windows, or the Goldilocks pressure and temperature conditions, this refers to the depth and temperature conditions necessary for oil generation. Barrel of sedimentary rocks below that oil window will break down the oil to produce natural gas, and therefore we're in the gas window. And so the oil window tends to be 2 to 4 kilometers. Below, deeper than that, if we hit a sedimentary basin deeper than that, we can generally going to produce gas. And so here we see sedimentary rocks formed in a depositional basin. And so if we produce oil and gas at the right, we have the right rocks and the right temperatures, again, those are migrating up. They'll tend to do so within rocks that are easy to migrate through, porous in the direction that they want to be formed. And then hopefully we get them into a situation where they get kind of trapped below something impermeable, and then they're stuck within what we call a reservoir rock, like that sandstone. And so here we have an anticline trap. So this would be a good place to drill down and suck out that oil and then gas as well if we wanted. And so we can get traps related to faults, proper orientations of stratigraphies relative to horizontal, and then also related to salt domes. So to be utilized, hydrocarbons must migrate away from the rocks where they're produced, the source rocks, and they got to be trapped in a reservoir rock. And they need to be nearer to the surface enough that they're able to be economically drilled. If it's too deep, it costs potentially too much money. And so those source rocks don't have high porosity or permeability, which is why they're not good for reservoir rocks. But the reservoir rocks, sandstone has high porosity and permeability, so the fluid can flow through it and it can store a lot of fluid. So here's a kind of just overview of the types of traps, where if we have a reservoir rock below them, the trap, which is also referred to as a seal rock. So we have a rock that's not permeable. It can seal that oil below. In a reservoir rock that is permeable and porous. And so in the case of an anticline, that material moves up above into the upper part of the anticline, but it is trapped here by the seal rock, both on the sides and above. And so that's why we can drill down and get in there. Faults can also produce traps. It's the fault acts as a seal on one side, and then we have a non-permeable rock above with dipping strata. Then we can get a little area here, a wedge of trapped oil and gas. On the sides of salt domes, which are interesting in and of themselves, when salt is under pressure, it begins to deform and tends to become buoyant as well and can bulge up into these domes. It's not permeable to the oil and gas, and so if it forms like basically an anticline with the seal rock, then on the sides of the salt dome we can produce and store oil and gas. And then if the stratigraphy is in this right situation where the reservoir rock pinches out against a seal rock, that can be a way to trap oil and gas as well. So the seal rock is really important. If we don't keep that rock sealed, then eventually that oil and gas will get seeped to the surface. And then at the surface, it can be biologically broken down and non-usable anymore. And so when we're looking for economic production of oil and gas, we're looking for all these structures that we just looked through. I'm going to skip ahead here. So oil and gas, this kind of took off in terms of being used. First oil well was drilled in Pennsylvania in 1859, and within years, thousands of oil wells were drilled. We look at what situations looked like. So these are actually pictures on the left here of oil production kind of along a fault zone, I think in Southern California, maybe in Long Beach, right here. And you can just see, wow, how many separate oil structures or derricks were needed to extract all that oil and gas. A lot of places, this was pretty unsightly, and some places just right on the beach, like here near where Los Angeles Airport is today, and some other places like that. Not the best. A lot of byproducts, so we can see here they're pumping oil, but there is also gas coming out, and it's just being burned off, i.e. pretty much wasted, but it's for the safety of that production. And so creation of an oil reserve is dependent on the right geologic conditions, as we saw, and the right timing. What we see today is what happened over the geologic past. And so if we get too many more deformation events, we could eventually like break the seal and lose oil and gas, or we could metamorphose the rocks and lose the oil and gas. And so oil reserves require a specific association of geologic materials and conditions over time. And there are favorable conditions. They may have existed, but they could also go away. So here's a map of oil reserves in North America, US, continental US and Canada and Alaska. And so we see a lot of oil reserves in the western kind of, not exactly western US, but the kind of border between the Plain States and the Rockies, and then also in the west side of the Appalachians, we see this area as well. And so the west side of Appalachians over here is good because it's not as metamorphosed. If you go a little further east, it was deeper into the tectonic belt of the Appalachians. A lot of metamorphism occurred, and so we probably lost any oil and gas that was produced there. Within this big broad area here, this was actually an area that was an inland sea over several tens of millions of years to hundreds of millions of years time. Not that long ago geologically, just about 100 million years ago. And so those rocks are still here. They never experienced much metamorphism or anything like that, and they're preserved. And so we can see they're kind of them by age. So we have a lot of Cretaceous age materials in some areas. We have some older Jurassic, Permian, and other types of rocks that have produced these oil reserves. And if we look wider afar, oil reserves are distributed on all continents, some onshore and some offshore. Regions bordering the Persian Gulf contain the world's largest oil reserves. So that's here. You can see Russia has huge oil reserves, the North Sea, North Slope in Alaska. You've probably heard of these. Texas, the Gulf of Mexico. Significant oil reserves in South America, off the coast in Australia, Indonesia, and some places in Africa as well. Generally speaking, so Middle East is the big player, 830 billion barrels of oil reserve. North America, 215. South and Central America, 332. So worldwide, we use, you can imagine this, 100 million barrels per day used by the world of oil. So it's insane. So we have to keep finding these oil and gas reserves in order to keep using it. We've projected out that it's probably about a 300-year time span of oil and gas, but we're still trying to find it. And so that takes a lot of seismic imaging, um, structural geologic expertise, and a lot of expertise with engineering and of oil rigs and drilling apparatuses. It's quite impressive. You can see the size of these oil rigs, what they have to do to drill down and get a lot of oil and gas out. You can see with just one oil rig, we can be economically productive, whereas in the past we had to have all those oil derricks to be economically productive. And so that shows we've come a long way with how we extract that material from even single drill hole with maybe lateral drills coming off of that. Once the hole is completely dug, drill rig is removed and the pump is set up. Oil is pumped out of the ground and stored in tanks and then removed, transported to where it can be processed to the different types of petroleum products that are utilized, whether that be for consumption in automobile or a different grade for an airplane, or jet fuel, etc. And that refining, is basically like producing an alcohol, right? You have you're heating up the material, and your certain products within that are going to come off at different temperatures, and so it's like a distillery, in this case for hydrocarbons. And so we can produce gas at the kind of lower temperatures, industrial fuels, lubricating oils, diesel and heating oil, etc. So we have examples of refineries right here. So we have Salt Lake's Chevron refinery right on site, in the north part of Salt Lake City. Gas is also an important thing, and it's more abundant than oil. It's also a cleaner fuel. But utilizing gas requires expensive high-pressure pipelines and ships because it is much more explosive and volatile, and therefore dangerous if an accident occurs in terms of explosiveness. But in terms of burning it, it tends to be much more clean. Other than oil and gas, we do have areas where that the reservoir rock sand containing oil has gotten near the surface. These are referred to as tar sands. Basically, there's residual petroleum in sandstone or sand near the surface. They can, because they're near the surface, there's a lot of bacterial digestion that's taken place. So lighter hydrocarbons, gas have been kind of eaten away. But these residual heavy oils, bitumen, is there, and that can be utilized, but it's too viscous to be pumped. So they have to be mined, and like we can see here with this open pit mine. And so we have huge tar sands in Alberta, Canada, and Venezuela, and these are they're being utilized today. We see it here, but they're not as clean of a production, and so it's going to be utilized, but it's not as priority as just traditional extraction because it is more expensive to process and also pollutes more. Also, if we have the source rock near the surface, that is called oil shale. It may not have yet turned to oil. It may still be waxy kerogen. You pick it up and smell it. It smells like oil. If we heat it a little bit more, we can get the hydrocarbons out of it. And so there's large supplies of this in Estonia, Scotland, China, Russia, and Western US. And even like on the border with Colorado and Utah, I believe there's quite a bit of oil shale around. And so that is likely to be used as we go into the future and the cost of these hydrocarbons goes up. Okay, so another fossil fuel is coal. Coal is black sedimentary rock. It's largely organic molecules of buried sedimentary remains of fossil vegetation that grew in swamps. This is an important global energy resource, but it's because of this, it's a dominant carbon dioxide emitter. And generally, while there's a lot of it, because it forms in lowlands of swamps, which are great depositional environments for rocks, and a lot of them have been preserved in the geologic record, we generally don't find it in rocks any older than 420 million years old, and that's because we know that land plants had not yet evolved prior to that time. And so they are Devonian rocks or younger, and then in the Carboniferous period, aptly named, that's when we find a lot of the coal beds around the world. Because the continents were in a good situation to be biologically productive. We had a lot of low-lying, swampy areas near kind of semi-tropical or tropical regions where we could have high biological productivity and store a lot of photosynthesis in the form of buried wood and woody material plants. So yeah, a lot of coal out there. It has many grades. So we'll talk about that here in a minute. So dead vegetation falls into stagnant, oxygen-poor water. That is important. The absence of oxygen prevents that decay by bacteria. Once that sediment, that organic sediment of the woody material is buried to depths of 4 to 10 kilometers, it compacts. And these are mostly stuff that's dying from year to year. So like mosses and leaves and things potentially falling into the water. So smaller stuff. Heats and compacts this peat. The chemical reactions of heat drive off hydrogen, nitrogen, sulfur as gases. But what remains is more than 70% carbon, and that's our coal. And so here's some pictures of some coal beds in Alaska. If you drive from here to Price along Highway 6, you'll see coal beds as you descend down into Price through the canyon. And so how do we mine these beds? Because they form in sedimentary layers. So this can be a tricky thing. So sometimes we're mining underground. You're basically extracting a layer, or you potentially remove everything to get at that coal. And then we're tearing up whole mountainsides to do that. So pretty destructive process. So here's a vast map showing anthracite and bituminous coal. So black, and then lignite, which is kind of like a less well produced coal. It's not as clean, not quite far along. And so we can see that this map there's a lot of it out there, a lot of environments where we'd form coal in the geologic past. So in this case, Asia is the huge region for coal production. We can see that on this map here. Consumption by region. Asia Pacific, 2,798 million tons consumed. North America is high, and Europe is high as well. Africa, no. South and Central America, no. And we can see why. They don't have many reserves. Okay, so coal mining depends on the depth of the coal seam. Within 100 meters of the Earth's surface, coal tends to be strip mined. Strip mining removes rock and soil overlying the coal seam and basically you just drag it out. Exposed coal is removed and the excavation is later then reclaimed. So basically buried, contoured back over once it's done. If it's deeper than 100 meters down, tends to be that it's underground mined. And so then you want to have a really rich bed or beds of coal and we'd tunnel through and extract the material. And this can be risky because sometimes tunnels collapse. Gases that are coming out of these coals can be there, which can cause people to be overcome and die. Also can lead to explosions because it is volatile and flammable. And this type of mining operation is quite dangerous and can have long-term effects such as lung disease as well. Okay, so we'll stop there, and then next class we will talk about some of these more renewable, although not renewable fully, but cleaner, non-fossil fuel products for energy. Go through this, and then we'll talk about ore minerals as well in class on Wednesday. Okay, so I hope this lecture was helpful for you to understand where fossil fuels are coming from. So if we go back, remember fossil fuels are coming to us from past life forms that were buried and stored within the rocks, either as coal produced from enough pressure and temperature to convert those woody plants into coal, or from phytoplankton, zooplankton being buried in clays in the seafloor, and then again being buried to the right depths, 2 to 4 kilometers down, to convert them to oil and potentially gas if it's buried a little deeper. Those products are limited, and then as we go forward in time, we'll see that we are living in what we would call probably in the future the oil age today. But this can't go on forever. We might be able to enjoy it for another 200 years if we're trying to, but we'll have to convert into other types of fuels as we move forward in order for society to stay at the level that we have today. Okay, so we'll stop here today.